Okay, so I have the same problem with the wireless microphone that I seem to have on a regular basis, and so it's not available. But continuing. So last week we had pretty much started all of the stuff dealing with Moody diagrams, all of the other fitting types that we could use, and we have completed probably 2/3 or 60% of the chapter so far. So Friday's plan is still to go to external flows and complete on by, for you it's Thursday, this chapter. So one of the things that we looked at the end of the last lecture was annular flow. That is, you have an object, say a cylinder within a cylinder. That cylinder, in this case, is attached to a tank. What reservoir level is necessary to maintain a flow of 0.01 cubic meters per second of water through the commercial steel annulus shown? The annulus is 30 meters long. You're given that the outer radius is 5 centimeters. The inner one is 3 centimeters, and you're asked to find QV, L, and all the rest. So this is where, if I remember to do this, hydraulic diameter starts to come in. And if you remember the relationships we got last time, hydraulic diameter, 0.05 minus 0.03, and you get a number that is 0.04. So the average of the two. The cross-sectional area is pi 0.05 squared, 0.03 squared, and you end up with 0.00503, and epsilon for steel is 0.046 millimeters. Okay, so meter squared. Make sure I got all that. Okay, so I have everything I need. Velocity, Q divided by A, 0.01 divided by 0.00503, or about 2 meters per second, coming out of that. So I have a velocity, Reynolds number based on hydraulic diameter is 1.9904 over 1 times 10 to the minus 6. $78,000. So this is turbulent. And remember, we have this magic line that everything separates between 4,000 and above as fully turbulent. We don't worry about transition, we just know that it's happened. Friction factor, epsilon over dH is 0.0115, and that yields a friction factor of 0.0232. And I'm going to say it's from the Moody chart. In all likelihood, I got this directly from the Holland equation. And again, you have a 2% error that's associated with the Holland equation relative to, say, the Colebrook-White equation, which is the basis of the Moody diagram. But to be honest, I can't pick out anything better than to the 1,000th or 100th place, really. And even there, I'm sort of pushing it. and that will equal 3.72 meters. So you can extract all the same thing. I haven't done anything different here than I did with regular circular pipes. I just put in the hydraulic diameter and did everything exactly the same as I did before. Any questions on this? It's all good? All good. So here's one where the solution or the problem is given in English units. And again, yeah, they're all used. They'd be no good. So you'll get a combination of numbers in this. Basically, it's 120 degrees Fahrenheit, which is 48, 49 degrees Celsius. Round pipe diameter of 0.2 inches or meters, and a velocity of 3.05 meters per second. All of those are sort of direct conversions. Surfaces are smooth, so epsilon over d is equal to 0. Through a transition, the flow enters a square duct with side A. And you can see sort of a very simplified image over there of that square duct. So it's expanded and it enters into that other region. Requirement, the head loss per unit length is the same in the pipe and the duct. Find the square duct size in meters. So if I look it up in charts, I'm going to get nu is equal to 1.89 times 10 to the minus 4th feet squared per second. And multiplying it across, converting it, I get 1.756 times 10 to the minus 5 meters squared per second. So this is, again, sort of matching with what was the original solution. So for the incoming flow, you end up with 3.5 times 10 to the 4th, so 35,000. So again, you know that's a turbulent number, and if you know it's a turbulent number, then you can start to use Moody diagrams. It's also smooth. So if I look at the Holland equation, there's the epsilon over d term that's normally there. If it's smooth, it's 0, and so that term doesn't play a role. So it's just log of 6.9 over Reynolds number based on diameter of the pipe. So friction of the pipe over diameter, v squared over 2g. It's all a bunch of numbers here. it's not a really good way to write the units, but the units are, so if I put the numbers in, I've calculated the friction factor within the pipe, that's 0.0224, substitute it in, and then the head loss per unit length of pipe is going to be Fp divided by d, v squared divided by 2g, and you end up with 0.0523 meters of head loss per meter of pipe. Any questions on this one? Still not done, but there's more to it. So at this point, we need to know what the mass flow rate is, because that's what we're going to put into this. And you end up by substituting in all the numbers, 0.09, 0.1 cubic meters per second entering into the square duct. So everything I've calculated so far is for the round pipe. Now I'm going to move to the square duct. So I need to calculate the hydraulic diameter for A over P, for A squared over 4A, and that will equal A. So that's my hydraulic diameter. The velocity in the duct, or square duct, I can call it S, Q over A, or Q over A squared. So the cross-sectional area is the same. It's just, so I end up with the same number, but that's volumetric flow rate per unit area. I don't know what the side length is. Head loss in the pipe is going to be Fs over A, 1 over 2G, Q divided by A squared squared. So again, I have all the information there. I have just substituted in everything, and I'm coming up with the same thing, except recognizing that this is now for the square duct, not for the pipe. And this head loss has to be 0.523, as I found out before, of head loss per meters of head loss per meter of pipe. So the Holland solution again looks the same. Again, I'm removing that roughness component because the roughness component is not playing a role since the walls are smooth. So it's just going to be 6.9 over hydraulic diameter. And so, there we go. So Fs over A, 1 over 2G, Q over A squared, squared, equals 0.523, and 1 over square root Fs equals 1.8 log of 6.9 A nu over Q. And I've got everything sort of set up. And those are your two equations. You have enough information at that point to iterate on. You make a guess, and then you sort of solve through for everything and check and see if it actually works. And this is the type of problem that's really good in Excel. Because if you do it in Excel, you can do infinite levels of iteration as you correct your friction factor and your value of A. So velocity in the square duct is going to be Q divided by A squared, 2.86 meters per second. Reynolds number based on hydraulic diameter, 3 times 10 to the 4th. And the friction factor is 0.0233. And so A over D is 0.186 divided by 0.203, which is approximately 92% of the original round diameter. Again, it's setting up the equations. That's the hard part. Using Howland equation, this is I mean, I skipped a lot of work. If I were to do it by hand, I'd probably take more iterations that I would take in a normal problem. Normal problems, you saw that most of the type 2, type 3 problems that we did, we could do in 2 to 3 iterations. Go ahead.
Why were you able to set the head loss in the pipe to the head loss in the duct? Are we just assuming that they're the same?
It was a given requirement. The requirement was that it had to be the same. So you were told in the beginning of the problem, requirement, the head loss per unit length is the same in the pipe and the duct. Was your question different?
So we assume the flow rate is the same because why exactly do we do that?
Oh, because the flow that's coming into the pipe, so no matter what I do in a pipe, so I have a pipe, I expand it, and I'll talk more about this. Q, Q here has to be Q here. Velocities don't have to be the same, and velocities are not the same because you have a much larger cross-sectional area or a different cross-sectional area. I mean, it's not a huge difference. This is not a significant change one to the other. But Q has to be the same in both cases no matter what. And that's a standard condition that we have imposed in all of the work that you've been doing since Chapter 3. Anything that flows in a duct has to be the same at the beginning and the end. Yes, you always make the same assumption unless there's a mechanism to allow air to enter or exit. So if I put a tank in there and I was turning it on and pressurizing the tank with the air coming by, then I would have less air coming in or less air going out than what I had coming in because I'm storing part of it. And you saw that when you looked at the conservation of mass equation. Okay. Okay, so just really quick notes on this. This is not a hard problem if you're doing iteration on a computer. It's a hard problem if you have to do iteration by hand. But you could always just add an additional term, and that would only change one of the equations. Both of these, again, because you're iterating and you do certain things, I'm doing a problem in SI that was originally set up in English units, and because it was set up in English units, I have an error associated with my answer versus what the English unit answer was. I accept that because my error is in the 100th place, and the difference is 0.03 inches, which is not a lot. So 3/100 of an inch, roughly whatever it is in millimeters. If roughness were non-negligible, you include epsilon over dH. Now, I keep saying, hey, I've used Moody diagram. I don't. None of the examples I do in this class ever use Moody diagram. I think I got called out for one of those last week where clearly the line was completely wrong. The answer was right. And you're going to find it's a lot easier at this stage, especially in my case where I'm trying to prepare notes, that I am not going to spend a lot of time looking at a Moody diagram. There's no point to that. So in addition to friction over the length of the pipe, and this is what we've always dealt with, was major losses. So we always call them major, or we will call them major losses. But in addition, real pipes have minor losses. And they come from things like pipe entrances, sudden expansions or contractions, bends, elbows, T's, other fittings, valves, gradual expansions or contractions, or sudden, both of those. So the nature of the expansion just changes what the loss is. These losses are generally major. So they really do change what you're dealing with, and we'll see that as we go through an example on that. But a partially closed valve can cause more pressure drop than a long pipe. They're relatively easy to deal with. You just add them up. We don't look very hard at this. We have K, which is going to be the head loss through the component divided by V squared divided by 2G, and you will get a whole set of tabulated values for each K associated with things. Total head loss is just going to be head loss due to friction, which is now a combination of the, what I'll call now major, and the minor losses, V squared over 2G. Major losses because usually we're dealing with very, very long piping systems. In short piping systems, they're of the same order as the minor loss. Values of K are tabulated in textbooks, engineering handbooks for various fittings, and what do I want to say other than that? Not much. It's in the text, and if you use any type of design software nowadays, it's already in there, and it's part of the calculation. I think I'm trying to remember what the piping network software is currently, but it's already done for you. Log law describes, just log law describes the velocity profile in turbulent pipe flow and leads to the development of friction correlation. Turbulent friction depends on both Reynolds number and the wall roughness. And you're now spending a lot of time. So we have a lot of errors associated with that, which we accept. We accept those errors because they're not as significant in the end in terms of how you calculate them. Colbrook equation is the fundamental formula, and the Moody diagram is its graphical representation. They are not the primary tools for solving pipe friction problems today. Generally, unless you you're really good with reading Moody diagrams, you probably are better off with either Howland or Swami Jain. Both of those will work very well. Solving for flow rate or diameter, which is the other type of problem that you've dealt with, type 2, type 3 problems, require iteration because the friction factor depends on the unknown. The last thing, and this is where we just started this lecture, hydraulic diameter is how we make the translation between circular and non-circular ducts. And it allows, in most cases, the use of the Moody diagram and corresponding Howland-Swami-Jain for any of these solutions that you need to look at. For real piping systems involve minor losses from fittings and valves, and they have to be considered. Okay, I'm actually going to jump up. Okay. And I already talked about that. There we go. So this is what's happening. So typically, if I had a nice, simple pipe, I wouldn't have anything in there. And so the flow would continue undisturbed. But because I introduce some sort of geometric change, I also introduce a pressure drop. And what you worry about is how that flow is changed. So this flow that goes in here has to accelerate and decelerate as it comes out. This one has to go around. There's recirculation that's going to occur in here, and then it will come out, and then there will be a separation and another recirculation that appears in there. And it's the same thing with elbows, especially if you have something where you kind of close it off. You have an acceleration, deceleration that occurs, acceleration and rotation of fluid that's going to happen. Same thing here, and even right here to a lesser extent. All of those cause a disturbance to the flow, and as soon as you disturb the flow, you change the pressure profile. Largely, we sort of don't do very much in terms of analysis of a valve or anything else. What we need to know is what kind of valve it is, what kind of elbow it is, and if it's a T. So T's are just generally something like this, where you have flow, say, coming in and going in two directions. And again, you'll have a recirculation that appears in there, and that's the sort of so you have two recirculation zones typically. Okay, so you have screwed valves, you have flange valves. Screwed just means that's a pipe that you sort of screw on. Flange means you attach it with bolts on both sides of it, and you then get a whole bunch of different K values. And as you can imagine, a bigger K value is associated with worse or more significant pressure drop. And so, for example, line flow, it's nothing. Elbows, 180 degrees, actually not too bad. 45 degrees are worse, and 90-degree regular is pretty bad. And one of the things you want to pull out from a table like this is to understand, or to sort of accept these are the numbers that kind of make sense in terms of what's happening. Now, as you go through all of this, and as you look at all of these numbers, you're going to have now a whole bunch of values where, or tables, where you have K, where you have K, and things like valve opening or fractional opening. So here on the left, you have three different types of valves: gate, disc, and globe. You can see that the K factor drops off significantly, even though the fractional opening, once the fractional opening is 0, you've got nothing out of there. With a disc, you have a little bit of flow that sort of sneaks through. And you accept that, and that's how you sort of make it all work. Any questions?
Would we need to know the different types of valves and what their names are, what they're associated with? Or, well, you probably would give us a schematic on the exam, right?
I won't give you a schematic. I'd give you there, and I'll do an example similar to what I would expect. I would say, just one second. I would say something along the lines of, this is a gate valve with 30% opening, and here's the table. There's a table somewhere. Or I'd give you the chart, but I'd give you enough information you could do it, not memorize.
Sorry, I can't discern which one's disc and which one's globe.
Disc and globe.
No, like which line?
Oh. Okay. Not a very good, oh. This is globe. This is disc. And this is a gate valve. I have to zoom it out, otherwise I can't tell the difference in colors. Similar things with butterfly valves. Again, butterfly valves are just gate valves that sort of twist, and valve opening degrees. I did threaten you with the effect of entrances and exits. So typically up to this point, we've had tanks and things that have flow through them, but when the flow has gone through them, we haven't considered what happens at the gate, or sorry, at the transition point between the tank and the pipe. And that's an entrance region. And one of the things that you find, and this is kind of useful to always keep in the back of your head, is that the more smooth edged, the better your results are in terms of loss coefficients. So you have exit losses of 1, but you can have sharp edged over here. You have R over D, L over D, K for those. And you have a theta, which is defined just as this right here. And you can see that by extending this, making it a smoother, longer curve, you have less exit losses. You also kind of run into another problem, which is that if you make it too smooth and too long, then you got to pay a lot for material. So the price, the decision you have to make as an engineer is often, how much room do I have? And if I have this much room, how can I sort of save things in terms of money? And I deal with an industry sponsor who's been very good, and his constant insistence on all of his work, and my students have spent years on this, is trying to make the device he's working on smaller, which means that we have lots of losses and lots of pressure losses, and I can't make it bigger to get around that issue. Same thing with sudden expansions and contractions. So here, again, one of the things that we've looked at are pipes that are coming in to one size pipe going into another size pipe. So on the bottom is a sudden contraction, flow is left to right. At the top is a sudden expansion, flow is left to right. And in the sudden expansion, you go from a small area to a large area, and you can see that you have a very high K for those values, and that they sort of normalize to each other when you get to a D over D that's close to 0.8. And you spend a lot, again, this is something that if it were on an exam, I might give you the chart, I might give you a number, I might give you something along those lines. Diffusers. Diffusers are gradual expansion designed to reduce fluid velocity. So, often you try and do something like this, where you smooth off the edges on over here, smooth off the edges over here, and that reduces your pressure loss. And by doing that sort of design, where you're giving nicely curved paths for the fluid to go through, and also avoiding a sudden sort of change, you do get better pressure recovery out of those. So efficient diffuser reduces head loss compared to a sudden expansion, thereby reducing the required pumping power for a system. But you constantly have clients who are going to demand, I want the thing to fit into a smaller space. Or I can't afford to pay for 100 meters of pipe, I'd rather pay for 10. And this is, again, sort of normal sort of things that you see. So here is a sudden expansion, or a diffuser, and you can see that K, which is on the left axis, is versus total cone angle. And you can see that if you can drop it to between, say, 5 to 15 degrees, you have the best sort of value because you have low pressure drops. If you increase it from 0 all the way to, well, 0 is there. Well, it's not 0, it's 1 degree. You have, for that total length, a significant changeover. So 0 is basically a sudden expansion. But increasing the length also means that you have a problem because you have a very long pipe over which you're doing this, and you have losses associated with that. And historical note, customers in ancient Rome used flared outlets, diffusers, to get more water for the same size pipe billing. So for years we've been trying to figure out ways to do things better. The loss coefficient is based on the inlet velocity head. So in this example, V1 is going to be higher than V2. Performance depends on the cone angle and the area or diameter ratio, And you can use empirical formula like Gibson's formula, K diffuser 2.61 sine of theta, 1 minus d1 squared d2 squared, y squared plus f average L over d average. So you don't get away from major losses, but you still have to deal with them. So with all of this, you end up with problems that you have to sort of consider. Hey, the optimal angle clearly from the chart is 5 to 15 degrees. If it's less than that, the diffuser becomes very long, and you have wall friction loss, the major loss, along the entire length. If you have it too steep and you start to go beyond 15 degrees, then flow can't follow the wall, it separates, and separation is sort of these rotating sections which I showed you in the valves, and causes large turbulent eddies and results in poor pressure recovery. So you're spending money on your design, and you're also spending money on material. So yeah, steep is great because you have less material. Shallow is not great because it becomes long and you have lots of material. But which point does one become better than the other? And it really depends on the power required for your system. Okay, water pumped between two reservoirs, 0.00566 cubic meters per second through 120 meters of 22 meters of 5.08 centimeter pipe. Compute the pump power required. Delta Z is 30.5 meters, so 100 feet, 400 feet of pipe, 2 inches diameter, and then a whole bunch of these things in there. So the pump is going to be a recovery, so it will add head to the system. So that's how you're able to drive it from point 1 to point 2. The distance between, or points 1 and point 2 are free surfaces, and they will be at velocity 0. So for this particular case, you have a whole bunch of elements. And yes, on a homework problem, it's perfectly reasonable to make you go through the entire book. And so if you look at that, it sort of ties it between sharp entrance, which is figure 621. And I'm using, I think, the previous edition of the book. I have not updated these for the current edition, so I have to be a bit careful. So these figures may not be the exact same figure numbers as before. I've run into this a couple times already. So I get K equals 0.5 for a sharp entrance. Open globe valve, I get 6.9. 12-inch bend, 0.25. Regular 90-degree elbow, 0.95. Half-closed gate valve, 3.8. And a sharp exit of 1. And I just sum up all the terms. And I have a minor loss of 13.4. Any questions so far? And so you're given the flow rate, 0.0566 cubic meters per second. You're given the diameter, 0.0508 meters, and velocity or volumetric flow rate divided by area, and you get 2.79 meters per second. Reynolds number based on diameter, velocity, diameter over nu. Put those numbers together. You get 1.39 times 10 to the 5th, which is 1.4 times 10 to the 5th. And from the Moody chart, again, I am lying to you, but F is equal to 0, 0.0216. And again, typically when I'm doing this, I'm using Holland. Actually, I did all of this with Holland. So compute the head loss. HF equals F L over D V squared over 2G. And that's 20.6 meters. Any questions so far? I haven't done the minor losses yet. So the pump has to deal with all of the stuff dealing or causing losses on this pipe or system. And free surface 2 is below or above free surface 1. So I got to pump up. So Z2 minus Z1. HF major plus H sure I got the right number, 13.4. I'm not going to do all the numbers here, but this is from that table, and it's equal to 13.4. 51.9, 13.4, V squared over 2G, and head for the pump is 56.4 meters. Now again, you have available to you, or you're asked to calculate the horsepower, and that's just going to be power of the pump, which is equal to rho G Q HP, which is equal to 3130 watts or 4.2 horsepower. So if you're solving through for this, you're going to get a value of 4.2 horsepower. And the reality is you can't buy a 4.2 horsepower. You're going to have one that allows for changes in efficiency, and those changes in efficiency are going to sort of require 5 to 6 horsepower. So 80%, 70, 80% efficiency. Any questions on this one?
So whenever you have dynamic pressure, it's always based on the inlet velocity?
Yes, so for a sudden expansion, yeah, for everything, it's the inlet velocity. Yeah, you're right. Any other questions? So here, I can start this problem. I think I may even end it, but we'll see. So since I like doing self-advertisement, this is a very simple diagram of a wind tunnel. And it's a closed return wind tunnel. And all that means is that you have a test section up here, and all of the fans and everything else are occurring there. There's a lot of things happening. Now, most research type tunnels, and there's one at the bottom, Roseburg 105, which is where I work, and that tunnel looks more like this. And so if you come in on the front door over here, you can see a test section, open area, there'll be pictures, and all sorts of things. And you have flow that goes left to right at the top, recirculates, hits a fan, goes through, and you'll notice that there are 1, 2, 3, 4, 5, 6, 7, 8, 9 sections there into which you have a flow. In this particular problem, you are given all of the area and velocities in the circuit. You have, and I will give it to you in a moment. Treat the four corners as mitered bends with guide vanes K corner of 0.2. The diffuser 0.6, nozzle 0.2, screens 4, and just because I can't get away with this, my tunnel doesn't operate that fast. Mine is operating at 18 meters per second, and based on a chord number of an airfoil, typically up to about a million Reynolds number. All right, so incompressible, I got to check for that, but yeah, everything works out really well. And you're asked to find, there we go, pressure rise across that fan. So if you remember at the bottom there was a fan, flow was going around it or through it, delta P, P1 minus P9, and the power added to the air in SI units. Steady, incompressible, negligible elevation change. Head loss is sum of minor losses. Tunnel friction, V at each section of the table, blah, blah, blah. Oh, one other thing. This is more like what we would ask on a final exam. So here's all the information, but that would be all it would be. Okay. So you have a whole bunch of pieces. You got corners, you're given 0.2, diffuser 0.6, nozzle 0.2, screens, and velocities to use in each of those cases. And where there's a cross-sectional change, you kind of have to deal with it. So diffuser, I think the nozzle really comes in and out, but that's okay. K of 0.2. Areas are given. Velocities at all of those points can be calculated based on this. Calculate all of the minor losses using the tabulated values, and you'll notice that at each of the sections, V7, V8, V2, V3 is used for that component. So I don't have a universal value, so I have to make sure I know what my velocity is at each of those points. And we calculated that in the table. And you continue with the rest of the tabulated values. Oh, so HL is 170.9 or 7 meters. Delta P is rho GHL, which is 2.1 times 10 to the third pascals. Calculating power, 46.5 kilowatts. We have very large fans and motors. V5 divided by C is approximately 0.18, which is less than that magic number of 0.3 where we worry about compressibility. And so if we don't have to worry about compressibility, everything sort of works out. We don't have to have a new look at this because continuity gets a little bit more hairy. And I think, okay, really quickly, there you go. Head loss as a function of velocity is shown here, so you can see how it changes.